Sarah. Okay. So yeah, I am incredibly honored to have the opportunity to be here to speak today. I actually have been working with some people here in this department for several months. And so it's really my great pleasure to have the opportunity to get to share some of my work more broadly. And then also, I think there's a lot of things about the research that we do in my group that has a lot of parallels to things that seem to go on in ISE, as I understand from my colleagues. But a lot of times we have slightly different types of processes and considerations. And so feel free to interrupt me at any time if something that I'm saying is not clear, especially if it's something where maybe we're using the same terminology, then I'm using it in a different way that maybe isn't familiar to you. Feel free at any point to go ahead and interrupt. So my work today is going to be related to smart manufacturing, and specifically to the issues of how in smart manufacturing, we want to move toward more and more flexible and profitable operation, more and more efficient, using more and more data. Then the problem can become, is that going to lead us to having issues with cybersecurity for our control systems? And what does it look like to try to consider cybersecurity as we're looking at the flexibility and profitability of our processes? And so my work focuses in general on control design and theory. So it's very math heavy, but at the same time, we try to look at industrial problems of interest. And so I'm in chemical engineering. So the types of processes that we control are really going to be things like large scale chemical plants or refineries, those types of things. And so when we have a chemical process like that, like a chemical plant or something similar, we're converting raw materials into products. And when we do that, we have a variety of operating objectives we want to meet, like meeting safety requirements, meeting environmental regulations, meeting our product specifications, and making a profit. So we want to satisfy all of these objectives simultaneously. We have to continuously monitor how our process is doing with respect to our objectives, and we have to do some external intervention if it's not meeting some of these. And process control gives us an automated method for that external intervention. So in chemical engineering, it is very common for us that our process control systems will be part of these types of feedback loops, which are shown here. And so the basic idea of a feedback control loop is that we have an output from our process, which for chemical engineers is something like temperature, pressure, concentration in a reactor, things like this. And we'll measure that with a sensor. And then the measurement is then compared against the set point, which is the value that we want our output to take. And then the error between the set point and the measured value of our output is communicated to the controller. And the controller uses some mathematical algorithm to determine what value of some input to the process to apply to try to reduce this error. And then an actuator, which for chemical processes, because a lot of times we're dealing with flows of different materials and pipes, a lot of times our actuators are valves. The actuator will then actually physically implement the input on the process. The big question in control design is, what is the mathematical algorithm that this controller is running? And so typically, or I guess many times in industry, that control algorithm will be something like a proportional integral derivative control law. And so that would have a form like what is shown here, where the input U for the process is equal to a function of the error EFT between the set point and the measured value of the output. And so this expression here includes a term proportional to the error, integral of the error, and the time derivative of the error is the name PID control. And so even though this has been very successful in chemical processes and is used all over, it does have some disadvantages in some cases. So for example, trying to tune this controller, like picking these values of Kc, tau, and tau d, typically employs a process model, and even then it can be challenging to get the best tunings. And this control law is sort of a one-size-fits-all type controller. It doesn't let you adjust it for different process dynamics beyond just changing these tuning parameters to try to get it to have the best response possible. And so to try to move beyond this and say, okay, well, for some processes, that's not ideal. What else could we do? People have over the last decades been developing model-based controllers. And so what that means is that now the control law is not just a one-size-fits-all thing anymore. It's actually developed to be explicitly related to your specific process dynamics. So it's supposed to help manipulate your specific dynamics at hand in a way that will give you your desired response from your process. So to do model-based control, we have to have a model. And so this model comes either from first principles modeling, For chemical engineering, it would be what we call mass and energy balances, which I'll mention a little bit more about that in a minute. Or we identify the models from input-output process data. And the model then describes our process dynamics, which is the variation of the process state variables in time to disturbances, inputs, and interactions between variables. And controllers are then made that are based on that process model. So in chemical engineering, a lot of times our models are nonlinear. And I'm going to explain that by first describing a very typical that we'll learn in undergrad in chemical engineering, which is called a continuous stirred tank reactor. This is one of the most basic reactor models in chemical engineering that you can have. And the idea of this is that you have this reactor, and there can be a heating coil with a heat rate Q being supplied to the system. There's a feed in and a feed out of this tank where there's reaction occurring in here. And the feed includes some reactant at a concentration Ca0. And then there's a temperature of the inlet stream, this reactor. Then you have an outlet concentration of your reactant species A, and then also a temperature. CSTR is considered to be perfectly mixed, has a lot of assumptions. And so then if it's perfectly mixed, the concentration of what's leaving and the temperature of what's leaving this reactor are the same as what's inside. So that's basically what a CSTR is in our chemical engineering education. And so even this system, which has many assumptions, very idealized, if we make a dynamic model for this system using what are called mass and energy balances, which essentially say the mass into this has to equal the mass out plus any mass generated, and then the energy in has to equal the energy out plus any energy generated. We get this system of equations, which shows how the temperature and the concentration of the reactant are changing in our reactor over time. If we look at the right-hand side of this differential equation, we can see these nonlinear terms involving exponentials that include temperature and then multiplied by concentrations. And so kind of crazy looking term. Where this comes from is this is actually the reaction rate law. And so in chemical engineering, a lot of times our reaction rate laws include nonlinearities. And as chemical engineering is really defined as an engineering discipline where we care about chemical reactions, in general, chemical processes, we get nonlinear models. But when we're designing controllers for chemical processes, we don't really want to have it be, okay, this controller for this process, then next process, let me redesign it from the beginning. We want to try to design general principles of controllers that can allow us to take a certain class of controllers and then apply it to many different types of systems. All could be described by nonlinear ordinary differential equations, maybe different nonlinear ordinary differential equations. So we have a general framework for describing their controllers. And so to do that, I'm going to introduce some notation. So here, X means the vector of the process states, which for this example would be things like temperature and concentration of the reactant in the reactor. And then we have U, which is the vector of the process inputs. So what that would be, it's something that I'm actually able to change. So maybe, for example, I can change a flow rate of fluid through this heating coil, which impacts the heat rate is being applied. And so maybe I say the heat rate I'm adjusting, and then that will be my manipulated input. Then the disturbance here, or W, is something for the process that is changing with time, but I don't have the ability to manipulate it as I want. So for example, say that I'm getting feedstock from some tank, and then maybe over time, composition of that changes a little bit because I'm taking it from different parts of the tank, and maybe that tank wasn't fully well mixed. Then in that case, maybe my concentration of my reactant in the feed is changing with time, and then that's like a disturbance. So now that we have that notation, this is what I'm going to be using in the remainder of this talk to signify a system of nonlinear ordinary differential equations, which can represent many process models that we use in chemical engineering. And so what this is that the time derivative of the states is equal to a nonlinear vector function of our states, inputs, and disturbances. And a variety of techniques have been developed for designing controllers for this type of class of systems, and model predictive control is the type that we work on. And I will describe model predictive control, but I just have to go through a few more assumptions that we're making before I do that. So first is that our state, our input, and our disturbance are all bounded. Then second, we assume that our process is stabilizable in the sense that there exists some control law that's an explicit function of the process state that makes our origin or steady state asymptotically stable, meaning that it will drive the state toward the steady state. In the sense that there exists a Lyapunov function V, for which the time derivative of this Lyapunov function is negative along the closed loop state trajectories under this controller h of x for all x in the neighborhood of the origin. And so what this means better shown in this figure. So the idea of asymptotic stability is that you approach the origin over time under your controller. If we think of this Lyapunov function like energy of our system, then it takes its zero value at our steady state or origin. And as you go progressively away from the steady state, it's increasing. And so what happens is if I am able to find a controller that makes this Lyapunov function decrease over time along my state trajectories, then what that means is that I must be approaching the origin under this controller, because the origin is where there is the most minimum value of this Lyapunov function. And so in this figure, I also denote this region omega rho in red. So this is a region where the Lyapunov function is upper bounded by rho, which is a number. This will be important in the remainder of the talk, and I call it the stability region. So overall, our controller h of x here does have a degree of robustness to disturbances and uncertainty, meaning that even when I have some plant model mismatch or disturbances, uncertainty, I'm still able to drive the process state essentially to my steady state. The drawback is that I'm not able to account for profitability explicitly using this controller, or constraints I might have for things like safety explicitly using this controller. That's where model predictive control comes in. So model predictive control is an optimization-based control design. What this means is it's a controller where the control actions that we're computing are actually the solution of an optimization problem. And so the optimization problem typically will have as the objective function, which is what we're trying to minimize, the time integral of a quadratic tracking stage cost. So this would have a form like ax squared plus bu squared if you have a single state and a single input. And then we solve our optimization problem every delta time units. So what this means is that in control, we want to continuously apply new control actions to our process, help manipulate the process in the best way over time. So at every sampling time, okay, here, we're going to take a measurement of our process state, compute a new control action using this optimization problem, then hold that constant for subsequent sampling time, which has length delta, and then resample the state, compute a new control action, and so forth. So this means that when we're computing the control actions, or when we're actually computing the solution of this MPC, we compute a piecewise constant input trajectory with n pieces, where n is what we call the prediction horizon, and each piece is being held constant for a period delta. So the idea is that the solution of this optimization problem is actually something like this dotted trajectory. It's a trajectory of what the input should be for my process with time, where for one time period, the input is held constant. Then I let it change at the next sampling time, then I let it change at the next sampling time, and so forth, all the way up here to the end of the prediction horizon. When we solve this optimization problem, what that means is we're finding the values of our input and make our objective function as small as possible, given that the predictions x tilde of the state vector have to come from solving this dynamic process model, and then that our inputs and state constraints have to get satisfied. And so typically, nonlinear programming algorithms would be used to solve an optimization problem of this type. And then a really important issue for MPC is the issue of feasibility of this controller. So whether or not there exist any inputs that can cause all of my constraints to be met simultaneously. And if not, that would be a problem, because that would mean I'm not able to meet my operating specs. And so the MPC has to be designed and the initial condition has to be chosen such that there are control actions that can allow me to meet all of my constraints and compute a feasible control action. So I mentioned that what the solution of this optimization problem is that it's actually a piecewise constant input trajectory that goes throughout the prediction horizon. So even though we're going to calculate what the input should be into the future for n time periods, we're actually only going to apply the first one to the process, because this model that we're using in our MPC is not perfect. And so as a result of the plant model mismatch, we want to take a measurement of our state, compute the best control action we can right now, apply it, and then discard the rest of our input trajectory that we computed. Instead, resample the state and compute a new optimal input trajectory, apply the first piece, and so forth. And so then it might sound like, okay, well, why are you going to compute the entire trajectory up to n sampling times into the future if you're only going to apply the first piece? Well, the reason is very similar to when you're driving a car that you look far in front of you instead of just like a foot in front of you. It's that you don't want to have short-sighted behavior when you're choosing what's the optimal thing to do right now. So overall, the objective function of this MPC takes its smallest possible value when x tilde is 0 and u is 0, which that happens at our steady state or origin. And so what this means is that a well-designed MPC should be driving our closed loop state to the steady state or the origin. When it does that, that's one notion of what we call closed loop stability in control. However, even though this MPC is supposed to drive you toward the origin, without a number of different theoretical conditions or extra constraints, you actually can't guarantee that this control law is going to drive you toward the origin. But MPC has worked pretty well in practice. And we also have a lot of theories about it. So that covers what MPC is. Now let's talk about how it's typically used in the chemical process industries. So typically in chemical engineering, it's part of a hierarchical framework that's shown here for integrating economic optimization and control. And so in this hierarchy, what happens is first, you compute the economically optimal steady state for your process to operate at. And then after you do that, send that economically optimal steady state to your controller, and then the controller will compute these control actions that will drive the process state to this economically optimal steady state with time. And so even though this is a way of integrating economic optimization and control, when we think about the goals of next generation manufacturing, like having greater profitability, greater autonomy, greater flexibility, separating economic optimization and control like this has been thought to be maybe not the best strategy. And so that led to the development, maybe around a decade ago, of economic model predictive control, or EMPC. And so what this is it's a way of trying to say, let's combine economic optimization and control into one optimization problem. Now we're going to have a model predictive controller. Instead of it having this tracking stage cost that's quadratic, trying to force us to operate at the steady state, we can give it any objective function we want, including ones that represent the process economics. So now my controller is explicitly all the time trying to optimize my economics online. And so what this leads to is potentially, I'm not operating at steady state anymore, but potentially that could be good in many scenarios. Like say that my objective function itself, my actual representation of my economics, is actually changing with time. Maybe there are changes in prices of things like my feedstocks or my utilities, like electricity. Or maybe I have time varying constraints. And so maybe I never really want to force myself to operate at any steady state. I just want to optimize my transient behavior. And it's cases like that where we would expect EMPC to maybe outperform this type of steady state tracking. But EMPC is really a generalization of MPC. So you could also say that a tracking MPC is also a form of EMPC, just with the objective function is now quadratic. So EMPC, because it's really just a generalization of MPC, has the form that is shown here, basically looks the same as the MPC we already looked at. Economics-based objective function, dynamic process model, feedback measurement, input and state magnitude constraints. And then this input rate of change constraint is not mandatory. The reason I added it here was just as a reminder that when you're trying to economically optimize your operation using a controller, you may have to add some other constraints to try to get that controller to have behavior that you like. So for example, if it's optimizing economic behavior by causing very significant changes in your actuators with time, maybe you would want to try to slow that down so that you're not wearing out your actuators. And so our group looks at a very special type of economic model predictive control for our cybersecurity work. And the reason that we do this is because this type of economic model predictive control has really nice theoretical properties that allow us to do a lot of control theory with the cybersecurity work, helps us better understand what guarantees we can make about when things are cyber attack resilient or when they're not. And so this formulation of economic model predictive control is known as Lyapunov-based economic model predictive control, or LEMPC. And so this is a two-mode control design. It was developed in the group of Professor Christofides at UCLA. And the first mode of operation requires that the predictions of the process state be maintained within this subset omega rho E of the larger stability region omega rho. And the reason that we do this is that it gives us a provable closed loop stability result where we can guarantee stability in the sense of boundedness of the closed loop state within this region omega rho over time. You can think of that like a safety guarantee. So I guarantee that, for example, my temperature of my reactor remains bounded with time. It doesn't go really, really high, causing many problems that occur when that happens, like a runaway reaction. And so we also guarantee there's always a feasible solution to this controller. We can also make some guarantees regarding the rate of change of the inputs between sampling periods. And all of these results hold even in the presence of sufficiently small disturbances due to the properties of the Lyapunov-based controller and the way that the constraints are designed to respect those. And so the second mode of operation of LEMPC is given by this contractive constraint shown in blue, which drives the closed loop state toward the steady state over time if you keep implementing this. So now I've covered the background on chemical process control, nonlinear model-based control, model predictive control, economic model predictive control, and Lyapunov-based economic model predictive control. I need to start talking about our work related to cybersecurity of process control systems. So as I mentioned, the motivation for this is a next generation manufacturing focus where a lot of flexibility, usage of data, and all of those types of things is very important. But as we try to use a lot more automation and a lot more computing systems, a lot more data, the potential that you can open yourself up to cyber attacks. And cyber attacks on control systems is a particularly problematic concept because if someone has access to your control system, they can physically manipulate an actual system. And for chemical engineering, that's often stuff that's very toxic, very hazardous, very problematic, potentially life-threatening to people. And so cyber attacks could impact safety, but also just go after profits or production rates. And so one question that should be asked is, does a cyber attacker really care about attacking a control manufacturing system? And I'm going to show a few brief case studies that show yes, they do. And so first, in 2009 to 2010, there was something called Stuxnet, which was a really big deal and has been in the literature about cybersecurity of control systems for a long time, because this was when it really became apparent that people could use attacks on control systems to actually cause physical damage of a plant. In this case, no one was hurt, but they were actually able to take down centrifuges using their attacks. And there was also a case in December 2015 where part of the Ukraine power grid was attacked. And there was a lot of things that happened: remote manipulation of circuit breakers, trying to prevent the operators from undoing attacks, turning off backup power for the operators, and then to try to prevent the operators from finding out that an attack was happening before they had finished executing it. They did a telephone denial of service to prevent the operators from getting phone calls. There was also in 2017 a case that at a petrochemical plant in Saudi Arabia was malware that could prevent safety instrumented systems from activating when needed. So for chemical engineering, this is very scary because our safety instrumented systems are a secondary layer of defense. So typically when we operate our processes, we have our basic process control system that's supposed to maintain everything in normal operating ranges. But if something is amiss, then what happens is there's layers of protection that we add on. And one of those is these safety instrumented systems that's supposed to do things like cut your feeds so that reactions will just stop. And so if you start attacking your safety systems, now not only could there be safety problems initially, but then even the backup systems that are supposed to catch those potentially are compromised. In 2021, there were two things that were big deals. One of them is there was a Florida water treatment plant issue where there was a remote user that went in and changed the sodium hydroxide level to be 100 times higher than it should have been. And an operator saw them remotely changing this and changed it back. And then also the Colonial Pipeline, where a company closed down a pipeline due to uncertainty as to whether operational technology was compromised after it had been clear that someone had seemed to get into their system and request money. So that highlights that cyber attacks are a real issue for control systems. And then because of that, we have to start thinking, okay, what are the types of attacks that someone could do on a control system? And so there are very many. As some examples, denial of service attacks, preventing parts of your network from delivering to others, eavesdropping, where an attacker could quietly learn about the system to try to prepare for a more active attack later, false data injection, where they give false data to something like your sensors or your actuators, time delay attacks, where they put in extra delay in your measurement or your control actions to try to destabilize the system, data tampering attacks, where data can be altered in storage or transmittal, replay attacks, where correct information from prior times could be sent again to make it look like nothing bad is happening, like everything is normal, when there's really things that are going on underneath that are problematic. And so the big problem is that cyber attacks on feedback controllers really destroy our whole notion of feedback control, which is that state measurements should be used to inform what inputs we should apply to the process in a good way. And when you somehow cut parts of the loop out in a control system, make it so the state measurements and inputs aren't related to each other anymore, and this does not lead to behavior necessarily. And so our goal is to understand how and whether using control theory to look at cyber attack handling could aid in providing security with some level of flexibility for next generation manufacturing. And so there are different ways that someone could try to attack a control loop. They could try to attack it more directly, like straight up go in and recode controllers, or try to put wrong signals to the actuators instead of the ones that the controller would send. Or they can try to do a more indirect type of attack where they send a false measurement to the controller, and then it goes through the controller's processing, and then that causes the controller to compute the wrong control input. And so because this is somewhat complex and there's many different ways that people can attack processes and many different attacks they could run at once, it's what we've been doing is trying to build from saying, okay, let's look at one type of attack occurring at a time. And then we're going to build up to saying, okay, what if multiple attacks are occurring? And so I'm going to start by talking about the type of attacks we looked at first, which is attacks on the sensors. And so in this case, if we want to say our process is resilient against any state measurement that's false, then what we would need to say is that there can't be any input policies that the controllers could use with their implementation strategies such that my state could exit a set of allowable states. But that's really not helpful at making any type of control design that does that. And so what we did first was we said, okay, let's just try something and see what we learn from that. So we're going to try something that intuitively seems to be beneficial, see whether it is. So this idea that we thought was intuitive when we started was to try to add randomness to the control law implementation. The specific reason we thought that might be helpful is that if we have a sensor measurement cyber attack, then what the attacker is really trying to do is achieve a certain input profile from that controller by providing a state measurement that they know will go through that control law and result in a certain control action being computed. And so the thought process was, well, that's sort of like them reverse engineering this control law, that because they know what this control law is, they can figure out what bad sensor measurement they need to apply to get their bad control action applied to my process. So what if I tried to confuse that? What if I actually had multiple different control laws at any sampling time I might choose between? And then I randomly select one of them. And then maybe now it will be harder for that attacker to figure out what state measurement they should provide to get a problematic input. And so before even trying to consider something like that, we first have to ask, during normal operation, can I do that? Is this going to be destabilizing to my normal operation? And we developed a strategy that was able to incorporate some level of randomness, but still maintain closed loop stability and feasibility during normal operation. And so the idea here was to develop a number of different LEMPCs, which I wrote here, NP of them, and also a Lyapunov-based controller. And at every sampling time, randomly select one of these until we find one where our state measurement is in the stability region of that controller. And so this does guarantee stability and feasibility, but it does not guarantee cyber attack resiliency. And so I can demonstrate this with a process example. And so in chemical engineering, for our control examples, we often love these PSTRs. And so this is that continuous stirred tank reactor I mentioned earlier, where we're having a certain type of reaction going on in the reactor. These are the dynamics of the system. And our control objective is to regulate this process in an economically optimal time-varying fashion while maintaining closed loop stability. And so here our economics is going to be defined by this objective function, which we want to maximize because this is the production rate of our desired product. We're trying to maximize the production rate. We also have manipulated input constraints, which are bounds on our inputs, which are the feed rate or the feed concentration of our reactant, and then the heat rate of the reactor. We take our Lyapunov-based stability constraints, where one of them sets the input corresponding to the reactant concentration in the feed equal to a steady state value. And then we also have a case where we have a controller for the heat rate input being set via Sontag's formula. And then we have a Lyapunov function. We design our stability region. And now we're going to make 6 LEMPCs, also a Lyapunov-based controller. So we're going to have 7 control options at every sampling time, no attacks. And in this case, we get this kind of crazy looking trajectory shown in the figure here on the right. And so the goal was that we never want our state to leave this largest blue region. And so we can see that we achieve that. The trajectory looks a little crazy, due to the random selection of the inputs at every sampling time, or the random selection of the control laws at every sampling time, but it still maintains the state within the large blue region over an hour of operation. So what happens when we add an attack? Let's compare the case when we have this sensor measurement cyber attack. We have a single LEMPC that we have the randomization. And does the randomization actually make it harder for the attacker? And so the answer is like really not really. Here is a bound on temperature that we set, and we say, okay, I don't want my temperature to ever go above that value. And it didn't go above that value in the prior simulations when we had no attacks. But then here we can watch that if we use a single LEMPC, pretty quickly, within approximately like 0.01 hours, the state goes above this temperature when we use the single LEMPC. And when we use a randomized strategy, it does depend on the speed to the random number generator, but even for cases where it waits a little longer, it doesn't wait that long. Maybe after about 0.03 hours of operation or something like this, it goes above the temperature. And so it doesn't really help then that we add the randomization for this specific type of randomization policy, because what we saw is that couldn't guarantee that there were no problematic inputs that could be applied over time. And so you could think of various ways of trying to modify this to try to do better, or maybe even trying to say, well, what if I don't want feedback at all? That would destroy everything that we ever tried to do about control. And so what's clear from this is that we need to have some new approaches. And so the next thing that we looked at is saying, okay, well, what if we still have our sensor cyber attacks? What if we look at several additional strategies for trying to control the process in the presence of the attacks, but we also add detectors? So here we're going to design the detection policies at the same time as we're designing the controllers, so that we can try to see if this simultaneous or integrated design and control policy or detection and control policy allows us to do any better than we did in the prior strategy where we just tried something out that sounded intuitive. And so in this case, we had an LEMPC that had random modifications to it to try to probe for cyber attacks. And this one had certain conditions under which we were able to say, okay, this is a cyber attack occurring, but we couldn't guarantee we would detect every cyber attack. And if we weren't probing for the attacks at the time, then we couldn't guarantee that we were going to maintain safety. So this didn't have the best security guarantees. We also looked at a case where we tried to say, what about a state feedback LEMPC, where there's an attack detection strategy based on state predictions at every sampling time. What that means is we control the process with LEMPC, but we look at the state predictions versus the state measurements, and we try to see if our predictions and measurements are close enough to each other. The problem with this one is that if all the sensors get attacked, then we can only guarantee safety for approximately one sampling period, maybe a little longer, after an undetected attack. And so we couldn't guarantee we always detect attacks, and then if we didn't detect them, then we couldn't guarantee safety for all time after. Then we also have this other one, this output feedback LEMPC, and this one is based on having redundant state estimators. And so I'll talk about this strategy more on the following slides. This one requires that we have a number of different sets of measurements, and that for each of the M sets of measurements, we're able to develop a deterministic observer or state estimator that's going to estimate what the state of the process is. And we have an assumption that the estimates are within a bound, in a norm sense, of the actual state after a certain amount of time, so that the estimates become pretty accurate. And so with that, we're now going to modify our LEMPC design to replace the state measurements with state estimates. And so just as if we had state measurements that were wrong, if we have state estimates that are wrong, we could compromise closed loop stability and our state could leave a safe operating region. So then we have to see, does the fact that we're using estimators allow us to detect attacks in any special way? Well, we noted that we assume that for all of our different estimators that we're using, that the difference between the estimate and the actual state has an upper bound after a certain amount of time. So this actually implies that there is a bound on the difference between any two estimates when we're not under an attack. And so we can use this to help us make a condition that will help us detect attacks. And so specifically, if at least one of our estimates is not impacted by an attacker, then if the difference between any two estimates is greater than the bound that should hold if there's no attack, we say, hey, there's an attack. If it's less than the bound, we can actually guarantee with this controller that we will still maintain the state within the stability region omega rho. So we still guarantee safety even in the absence or even in the presence of an attack that's not detected in this case. But the caveat is at least one of the estimates can't be impacted by an attacker, and we do actually have to have the ability to set up multiple estimates. So now that we've looked at several ideas for detecting sensor attacks, let's look at what's the difference between having sensor attacks and then adding actuator attacks on top of that. So having double attacks at once. And so in this case, we're again going back to our continuous stirred tank reactor, but I'm going to use a little bit different parameters here. I didn't write them before, so you didn't know the prior values of F and V, for example, but these ones are slightly different. We're also going to optimize our process economics, once again, with the same objective function related to the production rate of the product. We're going to narrow it down now to having only a single input to this process. So it is the concentration of the reactant this time, and Q, which is our heat rate, is fixed. We're going to use a slightly different Lyapunov-based controller and Lyapunov function. And then in order to be able to look at this idea of what happens if you have multiple attacks happening at once, we're going to look at the case where we have a specific attack detection policy, and then we're looking at the multiple attack case. So let's say that our attack detection policy, which is initialized at 0.4 hours when an attack begins, is that if our Lyapunov function value evaluated at the state measurement decreases over time, and we say everything is fine. If it's increasing, then we say, hey, looks like an attack over there. So is that an okay policy for us to use right now? Well, here is the case that we have no attack. It's given by this red line. This is the actual value of our Lyapunov function. And then over here, under blue trajectory here, it's also the case that we have no attack. And so in both of these cases, both when we're looking at the evaluations of the Lyapunov function based on the sensor measurements we're getting, and when we're looking at the actual value of the Lyapunov function for the actual state, both of them are decreasing. Therefore, the idea of looking at whether the Lyapunov function is decreasing or increasing over the sampling period would work for distinguishing between attacks and no attacks in this case, because in the no attack case, it is decreasing. So what happens if we have an actuator attack where we just put some wrong input to our process? So in this case, this is what the actual trajectory for the value of the Lyapunov function looks like. And then here's what the measured value of the Lyapunov function looks like from the state measurements that we're getting. Here, the state measurements are not compromised by a false sensor measurement attack. So in this case, we notice that the Lyapunov function is increasing, and we say, oh, that attack was discoverable. So then we also can say instead, okay, what if I'm getting false sensor measurements? So the actuators are doing fine. I'm biasing my sensor measurement for X1. And so in this case, what we see is that our actual state is following this, or our actual value of the Lyapunov function is following this dash trajectory here, which shows it's decreasing. And then over here, the measured value of the Lyapunov function is also decreasing. And so even though we do have the attack here, so that the value of the Lyapunov function here on the right is not the correct one, it still shows a decrease over time. And so we didn't discover that anything was happening here, but in both cases, it's actually decreasing. So when we say, okay, well, I didn't notice this attack, but it was actually decreasing my Lyapunov function. So then now let's look at combining these two. So now the sensor attack is occurring at the same time as the actuator attack. So in this case, here is the value of the Lyapunov function causing, the actuator attack is causing the increase in the Lyapunov function value. And then over here on the right, we see that we are increasing the value of the Lyapunov function with time. And so this one, again, is discoverable. And we say, okay, I caught that one. Now, what if it's stealthy? So in this case, the sensor measurements are going to follow the trajectory that they would take if there was no attack. So that's this trajectory here in blue. It's underneath the, that's this trajectory here in blue. Yeah, so the one that says no attacks is underneath this one. So that's how they are the same. But then over here, what's really happening is that the value of the Lyapunov function is increasing. So this is a problematic case. And this shows some of how cyber attacks are different from things like faults, is that typically when you have a fault, you're assuming that one, it's not malicious, trying to deceive you and cause many problems at once. And two, that you're probably not going to have the sensors failing at the same time as the actuators in such a way that one of them is covering up that the other one is failing. But that's exactly what's happening here, is that this is a non-discoverable attack. It's trying to actually make it look like the Lyapunov function is decreasing when in real life it's increasing and you're moving closer to the boundary of the safe operating region. So we then looked and said, okay, is there anything we can do to try to detect these simultaneous attacks? And so we looked at combining some of our prior detection strategies that we had used for state measurement cyber attacks only. And so in this case, for example, we can say, okay, let's have the redundant state estimators combined with looking at whether the Lyapunov function is decreasing over a sampling period, or having the redundant state estimators and looking at whether the state predictions match our state measurements over a sampling period. And when we do these things, then we're able to guarantee that under sufficient conditions, we actually can prevent a safety issue before we detect the attack. And there are some caveats there, though, like that we still need at least one of the estimators to not be impacted by an attack. And so potentially it could be challenging to get the reasonable control law parameters that fully satisfy all these resilience theories. But looking at what is a discoverable cyber attack fundamentally does help us with thinking of future ideas. So specifically, cyber attack discoverability would be whether you can actually distinguish between the state trajectory from the attack sensors or actuators and the actual state trajectory. And so what these integrated control and detection policies are attempting to do is to use a controller to force those differences to show themselves. Another word for something that is in the literature that you'll see that's related to this topic is active detection or active cyber attack detection. And so with that, I'm going to now move to something that in many ways is completely different. This is some of our more recent work where we're trying to look at implementing control on quantum computers. And so this really is completely different in terms of you could try to make some link with the cybersecurity and say, well, in some sense, with what I'm going to be describing, this is going to be another case where we're applying inputs to the process that aren't necessarily expected ones, but it's really not a cyber attack at all. It's just implementing control on quantum computers. So I'm going to begin with some background on what a quantum computer is and how it works. Information on quantum computers is stored in qubits, and qubits are the quantum computing equivalent of bits in classical digital computing. So it turns out that the way that quantum computing theory goes is actually done with a lot of matrices and vectors. And so, for example, this ket 0 represents the qubit is in the 0 state, and we represent that by a vector, which is this 1, 0 transpose. And ket 1 represents the qubit is in the 1 state, and then we represent that by a vector, 0, 1. And you can also have your qubit in a superposition state, which will have a form like this. So C1, 0 plus C2, 1. And the C1, you take its magnitude squared, and that's the probability that when you measure the qubit, it's going to end up in the 0 state. Same thing with the C2, if you take its magnitude squared, that's the probability that when you measure the qubit, it's going to end up in the 1 state. And so then, because those are the probabilities of it ending up in different measured states, when you take the two probabilities and you sum them, it has to equal 1. And so in quantum computing, you use a lot of logic gates, similar to the logic gates in classical computing, to try to transform qubits from one state to another and set up your circuits. And so here's an example of what it can look like. Have a lot of gates put together to form an algorithm on a quantum computer. And so I mentioned that in quantum computing, they usually use matrices and vectors to try to figure out what's going on in the quantum computer. So you will represent these different gates that are here with matrices. So this H, for example, is what's called a Hadamard gate. And this is represented by this matrix. And then this gate that's represented here, this is actually a series of gates. This is sort of a shorthand. But these are a series of gates that all have this type of form, where this is what they controlled phase rotation, and they have this matrix form. And so the reason that those types of gates that we just described are important for what I'm going to be discussing is that they're part of what's known as quantum Fourier transform-based addition. And this is an established algorithm, and it even has code that's available online. And we made use of this code in what I'm going to be describing with some modifications. And then this is code that is going to add two integers A and B. So you're going to take the integers, put them in their binary representations, do a lot of gates on the integers, and then eventually get back your qubits in a state where they are going to show you what the sum of the original two numbers would be in binary. And so Turns out the quantum Fourier transform based addition is actually deterministic. So in that case, I should have no problems calculating added values with that. So specifically, consider that I have this process. So here is a very simple single input, single output system, x dot equals x plus u. If I use u is equal to negative 2x as my control action, where I could calculate that 2x part as x plus x, that's where the addition is coming in. And as long as this is a deterministic calculation, negative 2 times x, then this control law will stabilize my system. And on a classical computer, I get this deterministically, no problem, stabilizing control law. But what happens on a quantum computer? So the algorithm that we just looked at, I said that that one's also deterministic. So in theory, I should be able to calculate x plus x, gate it, and then put that in here, and operate my process just the same as if I was using a classical computer. But today's quantum computers are not at the level of being fault tolerant yet. And so this raises the interesting question of what's going to happen if I try to compute control actions using a non-fault tolerant quantum computer. So that's what it has noise. And so what this means is that if control was implemented on today's quantum computers, noise could make applied inputs essentially non-deterministic or deterministic process behavior. So this raises the question of what happens when you try to put a controller on a quantum computer. And so because we want to look at the specific case that involves noise, we have to make a noise model. And so let me describe that first. So first, IBM does have available quantum computers and quantum simulators for the general public. There are also ones that you can pay for. We don't have access to those ones. But for the ones that are available to everybody, which anyone can go and make your own account and log in right now, and you can go run quantum computers. Then the quantum computers are 1 qubit and 5 qubit. And so this is too small for us to run our control calculations in any meaningful way. And so we can then use the simulators that they have, which are simulations of a quantum computer on a classical computer. And we can use these simulators, then try to see what if we had like a larger system, then we can look at having more qubits that are simulated. So the problem is though, that when we use the simulated version of the quantum computer, it doesn't inherently have noise anymore because the noise that's in the quantum computers is a result of the hardware. It's not coming from the actual algorithms that you're implementing on that quantum computer. And so as a result, when we implement quantum Fourier transform based addition using a quantum simulator, it's just going to be the deterministic result unless we add noise to it. And so to add noise to it, there are different ways. So you can do something that is available in the quantum simulator where it's a command called get the noise from backend. And so you can do that and you can try to pull in however they take this noise model off of an existing quantum computer, like the 5 qubit one. Or you can set different custom noise models, like a depolarizing error noise model. And so to do that though, and figure out what kind of noise level we want in our depolarizing error noise model, we wanted to try to have a benchmark against the one that pulls the noise off the back end. And so we had to choose a gate to use to try to compare these two different noise models. And so the gate that we chose was what's shown here. So this is a representation of a controlled Z gate, which is a special case of a controlled phase rotation. And we wanted to use that because the controlled phase rotations are generally in the QFT algorithm. And so here we compare the cases that we have here, our depolarizing error noise model, and then here the noise model that we got from the backend. And so this is the depolarizing error noise model, specifically with a depolarizing error parameter of 0.05. Because we saw a pretty good agreement here, we said, okay, that's going to be my noise model on my quantum simulator. And so with that, now we can actually run our simulations on our quantum computer or our quantum simulator with noise. So we're going to start our state at 7.4. And we're going to run the quantum simulators with what are called shots. So because there's potential for non-determinism and noise in a quantum computer, IBM has it set up so that you can say how many shots you want to run, which is the number of times you run the exact same thing again and again. And then what we're going to do is we're going to run our example on using the way you would do it on a classical computer. That's labeled classical system here. Quantum simulator with no noise. This is labeled as ideal quantum system. In this case, it really doesn't matter how many shots you do. It has no noise anyways, and it's a deterministic algorithm for what we're doing. Then the quantum simulator with 254 shots and noise. And so this is labeled noisy quantum system. And so the way that we're going to do this is when we run the 254 shots, then we're going to take the one that had the most counts, which is one of the functions that we use to try to say, okay, we're going to take an input that appeared most often. And so we can see here the results. So the quantum and the ideal, or the classical and ideal quantum systems are the same. And that's because, like I said, the quantum simulator with no noise is going to do the same thing as the classical one in this case, because the algorithm is actually deterministic for QFT. And then here we see the results with the noisy quantum system. So we still drive ourselves to the steady state with time, but it's a little bit offset from the others. So what happens if we lower the number of shots? And so now we can see that it doesn't look as good, a little more off compared to the case where we had more shots. And then we can say, well, what happens if I make another change? What if I actually change the initial condition? So here I change the initial condition. I start much closer to the steady state. This was important because the way that we were implementing the quantum Fourier transform-based addition says how big is the number that you're trying to add. And so actually, as you get closer to the steady state, we actually are using less total qubits in the quantum Fourier transform-based addition, and this has some level of impact on our results. And so then here we have one shot, and we can see that close to the steady state, it's not doing too bad. And then if we put 254 shots and we start at this initial condition, we actually are able to overlay all the results. And so in conclusion, next generation manufacturing requires flexibility and profitability, and it's facilitated by automation advances such as economic model predictive control. But flexible and profitable systems might not be secure. So attacks on control systems could undermine process safety. We've been looking at integrated detection control policies geared toward nonlinear systems, which have the potential to enable attacks of various types to be detected before they cause safety issues. This does require a lot of control-theoretic guarantees, which may be hard to get in real life. And then also, it may require at least some sensors to be secure, or we would expect that if we handle attacks after detection, that we would need at least some actuators to be secure. So fundamental notions of cyber-attack resilience and discoverability for nonlinear systems are helping to provide us insights into potential future directions, developing secure controllers. And quantum computing provides another interesting potential direction for the future of next generation manufacturing. We don't have any guarantees right now that it's going to be giving us any better algorithms from a speed perspective. And so more what we're hoping to do with this work is start to probe some of the theory that's related to this from a control perspective, and maybe that will inspire algorithm experts to come up with some new algorithms that we could use. And so we'd like to thank our financial support, the NSF, Air Force Office of Scientific Research, Wayne State University Research Grant, engineering opportunities for engineering undergraduates, grants boost funding, startup funding, and then also I'd love to thank my great research group. We have 6 awesome PhD students, and we have other undergrads working on things, and the people whose work you saw presented today, they're listed here. I'm so grateful for them. And thank you all so much for your time and for this great opportunity to talk in this department, and I'm really happy to take any questions.